In the last video, we saw one way of visualizing the solution to this system of differential equations. Namely, we figured out how we could plot as a function of what time was, as a function of how long it's been since this started, we plotted the populations of the worms and the populations of the robins. So here in red, we might have how many robins we have, blue is how many worms we have, and we can see that we have this oscillating effect where these two populations cycle sort of slightly out of sync with each other. And this is great. This is a way of visualizing what's happening. But there's another lens through which we can view this. Rather than plotting the W, the population of worms, with respect to time, we're going to plot the population of robins with respect to the population of worms. So to do this, the thing that we really want is dr dw. And so what this is, thanks to the chain rule, this is dr dt over dw dt. And for simplicity's sake, we're going to ignore these constants a, b, c, and k. We're going to assume that all of these things are just one. Again, these things encode things like what the units are, what the growth rates are. We're just looking at the general shapes. So for now, we're going to say a equals 1, b equals 1, c equals 1, k equals 1 to just ignore these things. Okay, so because of that, we can just write down what dr dt is. Dr dt is this. With the ones, we get negative r plus wr. And in the denominator, we have w minus wr. Cool. So this is dr dw. This is a perfectly valid differential equation. We now only really have a pair of variables. This is sort of the normal type of differential equation we've been talking about. And probably the easiest way to understand what's going on here is to look at a slope field. Okay, here's a handy dandy Desmos slope field generator where I've plugged in the differential equation that we just said. So we have negative r plus wr over w minus wr. And this differential equation gives us this particular slope field, and we can use this to understand the interrelationship between the worm population and the robin population. So we're plotting worm population on the x-axis, robin population on the y-axis. And in the GeoGebra video that we did, our initial condition was, well, what if there are 1.3 of each? So that's this point here. We have 1.3 of each of these values. Well, we saw that our rate of change in the robin population was actually going to be increasing, while the rate of change in the worm population was decreasing. In other words, we were moving in this direction. And so we want to know, all right, what does a trajectory solution to this in this slope field look like? Well, that's just going to be something that traces out. This is going to be really questionable here. The idea is that we go with the flow and we trace out the curve or the solution to this system. And the general idea is that when we are down here, we don't have many robins or worms, which means, well, since there aren't many robins to be eating the worms, the worm population is going to be increasing. And then as the worm population increases, the robin population starts to increase as well. And that's going to cause the worm population to decrease. And we end up going around and around in this circle. So this curve is the solution to this differential equation. It's this oblong circle looking shape. And the fact that the way we're viewing this in the other interpretation were these sine looking functions. Now we've got a circle that we're basically going around in circles about. And one nice way of viewing it like this is that we can imagine if we started off with a different initial condition. Let's say we started off with let's say two worms and 2.5 robins. And again, units are weird. We're probably more talking like 200 worms and 2.5 dozen robins or what have you. But given the setup, if we had a whole bunch of each of these, that's going to cause sort of more drastic swings. And we can see that by tracing out what this curve looks like. It's going to look something more like this, where we end up getting fairly drastically low numbers. Oh, this is really bad. Pretend that I didn't just cut across 7 lanes of traffic there. But because we started off with sort of extreme values, we end up getting these very wild swings back and forth. Right? And I want to contrast to that, well, if we start off at that 1-1 solution, remember in the last video, we saw that if our initial condition was 1 and 1, rather than being these oscillating values, it was just a straight line. In other words, it doesn't have anywhere to go. There's one of each. Everybody's happy. There's no cycling going on. This is a stable solution. So this point is called an equilibrium solution. And it occurs when we have, when we have this balance between everything that's going on. Okay, so this is called the phase diagram. It's another way of visualizing how if we have a system of differential equations, how these different populations can interact. And it can sometimes show us things that just the graphs don't quite get at.